All right, let's talk about chapter 17. We'll do this today and Monday. I mean, I won't go beyond Monday because chapter 18 needs 2 full days for proteins. That'll be Wednesday and the next Monday. Okay, now chapter 17. Students find this a little challenging in this regard. Chapter 16 is somewhat organized. It's saccharides, and you got carbonyls and hydroxyls, and you have 5 or 6 carbons long, and the saccharides have some similarities to them. You saw that. Proteins, chapter 18, amino acids. There is a very similar structure to all amino acids, with then in our group coming off the side that distinguishes one amino acid from another one. Okay, in the middle of this now, we've got lipids. And what are lipids? I'm going to have a slide that kind of help you wrap your arms around what they are. But bottom line, they are anything, any biologically active molecule that is not soluble in water. These are non-polar molecules. Olive oil is an oil. We say olive oil. Well, we say this is coconut oil, but coconut oil is not an oil. It's a solid. You got to heat it up. You heat it up and you turn it into an oil. So, but we would say this is a fat.
Yeah, it's like lard.
It's like lard, coconut oil. Saturated, unsaturated. Okay, we're simplifying things here. I'm going to show you in a second that there is some saturated fatty acids in here, but a lot of unsaturated. It's not just like it's all unsaturated. We'll see in a minute. All right, but these I brought a couple other things from home. Vitamin D, which is a liquid. It's a fat. And actually, if you look at the ingredients back here, it's vitamin D, and the other ingredients are medium chain triglycerides. MCTs. Here's a bottle of MCTs. Liquid coconut oil. So that's liquid coconut oil. And this is non-liquid coconut oil?
So what do they have in the liquid coconut oil?
Excellent question. Don't leave here today without knowing the answer to that question. Okay? Because we'll get to it.
You're welcome, class.
We're going to get to it. What is the difference? Well, one difference is this is a liquid, this is solid. What makes this a liquid? It's coconut oil. What makes this a solid? It's coconut oil. Okay, Cameron, don't leave here today without knowing the answer to that question. Okay? All right. All right, so let's get our arms around lipids. That was just a teaser. Okay? When you watch a trailer for a movie, you just saw the trailer. Okay? Lipids. Sorry, I'm bouncing around here. Lipids. An energy source. Okay? Don't get down on lipids because they have higher calories. Don't get down on that. I take this stuff here and scored it on my quinoa. Last period they told me I was pronouncing it wrong. Quinoa. Quinoa? Quinoa. Quinoa. Okay. Okay, to me it's quinoa. It's going to always be quinoa to me. It's too late. I'm unteachable. Okay, but I put that on my breakfast bowl of cereal or whatever. A little bit of this. It's what keeps me having energy at 2 in the afternoon. But it's more than energy. I told you vitamin D, A, E, D, and K are fat soluble. They actually don't absorb into your body as well without a little fat in your diet. You get a little fat in your diet and you absorb some of the necessary nutrients that are not water soluble. They're fat soluble. And the fat in your diet is actually helping transport them into your body. Okay, this is a good slide to wrap your arms around a little bit to just kind of I said lipids are not water, not soluble in water. So what are they? Well, here we're going to try to touch on all these classes of lipids. We're going to, so saponifiable, non-saponifiable. You already are familiar with that terminology. You've heard of what? Saponification, which is the reaction of an ester with what? A strong base. Sodium hydroxide, potassium hydroxide, that's saponification. So we're not talking about what your body would do with these things, but if you had this lipid, you could saponify it. We're going to look at that reaction eventually. All right, so this and this we're going to talk a fair amount about. Here is a very simplified drawing of a triglyceride. It's got a glycerol backbone with 3 fatty acids attached to it. Here is a similar simplified drawing of a phosphoglyceride. Look, if I didn't have this on here, you see the similarity so far? Glycerol backbone, 2 fatty acids, and then phosphoglyceride. Phosphorus. With something here, X. X varies. You define the X, you know what phosphoglyceride you're talking about. You have to define the X and what fatty acids are on there. All right? So you see the similarities? Okay, now, both of these have fatty acids in them. So we need to now kind of step back before we build these molecules. Let's step back and get an appreciation, a more of appreciation for what a fatty acid is and the properties of fatty acids. Look at that. I got that circle on here, that drawing on the board. Diversity. Should have drawn that on here. Right, so that's where we're going. So we want to look at fatty acids and drill on up into here. This is saying it's simple. Why? Because it's 3 fatty acids. This is a little bit more complex. Yeah, you've got pretty much the same backbone, plus you've got the phosphate ester on here. So it's a little bit more complicated. So the fatty acids. You can thank the previous class for building this molecule for us. 18 carbons long. You gotta pay attention, Samantha. You get hurt. 18 carbons long. Carboxyl group here. Oxygens. Some polarity here. Some water solubility or ability to associate with water molecules here. And very nonpolar tail. Long. You know, we looked at hexane and other little molecules. Now we're looking at a pretty big molecule here. 18 carbons long. And this is one of these. One. Not 3. This thing has 3 molecules like this on it. So there's your fatty acid. Saturated. What's that mean? All single bonds. Now we're not talking about this one up in here. Just on the carbon chain, the carbon chain is saturated. Single bonds. And 18 carbons, this is what acid? Stearic. This is stearic acid. 18 carbons long, saturated fatty acid. Polar head, carboxyl group, nonpolar tail. Okay, they're long-chain carboxylic acids, 10 to 20 carbons long usually. They can be less than 10, and they are usually even numbers of carbons. So there's not like an 11 carbon fatty acid. There's 10, 12, 14, 16, 18, 20, 22, 24. I think I mentioned the movie Lorenzo's Oil.
Yes.
Did anybody watch it? Have you seen it? Long time ago. Lorenzo's Oil has to do with a true story of a little boy at the age of probably 8, 9, 10 years old. They realize he has a genetic flaw in terms of being able to digest long-chain fatty acids, and they're building up in his body. And it's what's kind of interesting about that disease is it does not manifest itself until the boy, and it's usually boys that are 8, 9, 10 years old. So this little boy is developing well, he's happy, he's good, he's active, he's energetic, and he's 8 years old, and he starts his mental you start seeing mental deficiencies, attitude problems, all kinds of things coming in because he's building up long-chain fatty acids in his body, and it's starting to affect his physiology. So I think the library has it. Get a box of Kleenex, and yeah, it's a sad story. It is a sad story, but it's a remarkable story in terms of the parents and how they really dig into this and try to figure out what's going on, and actually do figure it out better than the medical community is able to figure it out at the time. We're talking, what, like the 1960s and 70s?
What, the movie?
Yeah.
Or the scenario? I think it was early, like 1980.
Like 1980?
Yeah,
okay.
Real early.
Yeah, because the boy actually just passed away in the last 3 or 4 years.
Basically, vegetable state by the time they finally found not a cure, but something that slows the process or
Right,
the process,
right.
But others are able now.
So it's a worthwhile movie. Okay, now let's take a look at these. We looked at stearic acid just right now. This is stearic acid. Saturated, 18 carbons. Oleic acid, unsaturated, 18 carbons. Now notice there's 1, 2, 3, 4, 5, 6, 7, 8, but there's 7 of these CH2 groups. And then your double bond, and then 1, 2, 3, 4, 5, 6, 7 CH2 groups, and a methyl group. 1, 2, 3, 4, 5, 6, 7. So I'm going to split these 2 carbons out of here. I'm going to put a double bond in here. This is, you know me, I'm amazed by all this stuff. What amazes me about this one, that double bond can be anywhere. But it isn't anywhere. It's right there. 7 carbons on one side of it, 7 carbons on the other side of it. There it is. Would you like it if your elbow was just anywhere between your shoulder and your hand? You wouldn't like that, would you? So where your elbow is not just a random event. Your elbow is right there, right in the middle of between your arm and your shoulder. Well, there's a reason why. The nature doesn't just put a double bond somewhere. It puts it right there. And it is kind of like an elbow. It's a place where the molecule comes down and bends. That is a cis double bond. Comes in one side of the double bond, goes out the same side. It doesn't just say, well, let's put a double bond. No, we're going to put a cis double bond. Where? Right in the middle. Okay? So, it's pretty amazing. Now, let's make it trans. I'm going to make this bond trans. That will be a trans fat. Okay? No trans fats on all the labels. So if you hydrogenate this thing, or actually if you partially hydrogenate this, you toss in a platinum catalyst. The platinum catalyst might come along here and associate with this double bond. No hydrogen around, it flips the double bond around to trans. So partially hydrogenated fatty acids probably have some trans fat in them. What's the problem with trans fat? I'll have a slide here later that will show it. That is now hanging pretty much the same way as stearic acid. See, it comes down, it comes into the double bond, it goes out the other side. That's just what single bonds are doing. Come in and zigzag and zigzag. So the trans fat, it zigzags through the double bond. The cis doesn't zigzag. It comes in one side and goes out the other side and makes an elbow in the molecule. All right? This is a trans fat. The other way you get these is by cooking. So you cook with olive oil, and you could mess up the oleic acid in a couple of ways. I think you could isomerize it. You can certainly oxidize it. It can react with oxygen if you cook with it at too high temperatures. What did I do here? So let's get it back to be cis. So that's what you want. That's what exists in nature, are cis. Just to put it down here, if we were to do I think we've done this before. If we were to do a condensed formula, it would look something like this. All right, so you got 7 CH2s on one side of the double bond, 7 CH2s on the other side of the double bond. 7 and 7 is 14, 15, 16, 17, 18 carbons. Let me get a little better C right there. Okay, so we have saturated, no double bonds. Unsaturated contains double bonds. Oleic acid is mono unsaturated, only has one double bond. And it is the cis configuration. All right, I want you to appreciate something about melting points. Okay, this is a liquid at room temperature, which means its melting point is below room temperature. All right? At room temperature, it's already melted. It's a liquid. This is a solid at room temperature, coconut oil, which means that its melting point is above room temperature. We haven't reached its melting point yet, so it has not melted. Double bonds lower the melting point. Unsaturation lowers the melting point. Okay, there's a slide coming along here. I think these slides are a little bit, we'll look at it in just a second. But there's your stearic acid, there's your oleic. So this would be stearic, saturated, oleic, unsaturated, cis. Here's another slide showing it. So there's your oleic, cis, and this would be the trans. Okay, do you see the trans? Boom, 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 boom. So it is looking like stearic acid. The trans doesn't distinguish itself a whole lot. It does have the double bond, and that double bond will react differently than a single bond, but the actual shape or configuration the molecule can get in is very similar to the stearic acid. Okay, here's melting points. Nowhere on here does this say melting points. Melting points. All right, so here, this is room temperature here. So below here, we've got liquids. And above here are solids. Let's just look at this line for a second. Don't get all, let's just follow this line. What we're looking at here is the temperature at which this would melt, and as a function of how many carbons long the fatty acid is. So it's 4 carbons long, it's melting at about minus 5 degrees centigrade. 6 carbons, 0 degrees centigrade. 8 carbons, about 18 degrees centigrade. 10 carbons is going to be a solid. All right, at 10 carbons, that fatty acid is melting above the room temperature, so it's going to be a solid. 12, 14, 16, 18, right here. Here, okay, we've got stearic acid there. Oh, sorry about that. Stearic acid, 18 carbons long, saturated. Oleic acid, 1 double bond. And look at it. It is a liquid. That's not oleic acid, but there's oleic acid in here. It's a liquid at room temperature because its melting point is like below 20 degrees centigrade. The room temperature is about 22 degrees centigrade. So it's down about 18 or so, and it's a liquid.
So they're adding the acid. Is that what you're doing there?
Here, this is a triglyceride, but it has oleate on it. So it doesn't have, oleic acid has linked to glycerol to form the oleate ester. Okay, so it doesn't have a COOH on it.
Okay.
It's linked to the glycerol as an ester. But here we're just looking at the fatty acid all by itself. So 1 double bond, 2 double bonds, 3 double bonds. As you add more unsaturation, you lower the temperature. 3 double bonds here. Melting point is down around minus 10 degrees centigrade. Omega-3 fatty acids are polyunsaturated fatty acids, usually 3 double bonds. Polyunsaturated. They have melting points down around minus 10 degrees centigrade. Now, if you were a salmon swimming out in the Pacific Ocean next to an iceberg, salt water, it's probably minus 3 degrees centigrade is the melting point, or the freezing point of that water. Would you want this floating around in your bloodstream? Or would you want something like fish oil floating around in your bloodstream? Where do we get omega-3 fatty acids? Fish oil. You get it from fish. Do you see why? That they have triglycerides. They need triglycerides. They have them floating around in their bloodstream as a liquid. Why? Because of the double bonds that are on the fatty acids that are on that triglyceride is what's keeping those liquid. All right? And you need that fish oil. You need it for your cell membrane. So you kind of need to get it. You could eat plants if you're against eating animals. You can eat flax. You can eat plants that have omega-3 fatty acids in them. But you got to get omega-3 fatty acids. And you really should be getting them. I remember in one article they were saying it's kind of like the fertilizer for the brain. Omega-3 fatty acids. Fish oil, things like that. So I give the salmon, they get an A in biochemistry as far as I'm concerned, because they chose the right fatty acids. Okay, let's get to our triglycerides. They're going to be esters. They are actually triesters. Okay, what do I mean? They're going to have 3 of these kind of bonds between the glycerol and the fatty acid. There's an ester linkage. Okay, so let's get familiar with the triglyceride. First of all, you need a 3x5 card for this. You can see the importance of this backbone. This is it. It's a pretty simple molecule. Another way to draw it would be just simply like this. You got 3 carbons. You got an OH group on each carbon. And hydrogens filling it out. It's a triol, glycerol. We came across this in chapter 12, and I said, you know, you'll get more familiar with that molecule in chapter 17. And this is why. Because it's so important to the triglyceride backbone. Glycerol. Okay, now, so that is kind of what's bunched up in here. This is why I'm saying the backbone. It's what's holding this triglyceride together. And it's holding it together with 3 ester bonds. Here's your fatty acid, but it's not in the acid form anymore. It's in the ester form. Through esterification, it's reacted to the OH on the glycerol and formed an ester. The other OH on the glycerol formed another ester, and an OH on the other glycerol formed another ester. It is a mixed triglyceride. Mixed. What do I mean by that? These 3 fatty acids that are on the triglyceride typically are all different. It's not all stearic acid or oleic acid. When I say there's oleic acid in here, that's not the only fatty acid in here. It is one of them. All right? So here's would be the stearic acid, stearoyl. So they're the stearate form of it, linolate form of linoleic acid, palmitic palmitate form of palmitic acid. So 3 different fatty acids. And here is showing the reaction. Here's your glycerol, fatty acid. In this case, just for simplification, they're showing it as 3 stearic acids. And the carboxyl group is reacting with the OH to form the ester. And you got this triglyceride. All right, and there's the kind of the generalized drawing of it, just so you can see the major components. Glycerol backbone, 3 fatty acids, and compare it to phosphoglycerides later. All right, so from plants and fish, they're oils. Animals, they're usually fats. I think we have a slide. Yeah, here's a good slide. This slide is comparing olive oil with lard from beef fat. And what we're showing here are the 3 different fatty acids that are in here. Now this one would be more like your oleic. See, it's saying it's unsaturated. All right, so what is that telling you? Well, even lard has some oleic acid in it, but it is a minor component, and stearic acid is the major one because that is saturated. It is a solid at room temperature. It's kind of dominating the melting point of the beef fat. Olive oil, oleic acid is the dominant fatty acid, and it's dominating the melting point. It's having a big influence on what the melting point of this is, and so it's an oil at room temperature. All right? You could do this if you're familiar, if you're curious about any oil, rapeseed oil, sunflower oil, whatever kind of oil you eat or like to eat, any from walnuts, from cashews, whatever. You could go in here and find out what is the triglyceride in any one of those things, and it'll show you the 3 different fatty acids that make it up. It's not hard to get online and just find that information, just pretty much like that. What are the 3 fatty acids in the triglycerides that are present in walnuts? Or not, don't do it now. but you can do it, okay? So if you're interested. And soap makers, actually when we make soap, and that's what we're going to do at 2 o'clock here, we're going to make soap. This gives you the suds. This is what makes suds. This is what makes it moisturizing. Palm olive, that old soap that used to be something palm olive soap. It's palm oil and olive oil was in palm olive soap, and then maybe some coconut oil. I don't know what they did, but it's creamy and moisturizing. That's what you get from olive oil. And canola oil is cheap. So you get the suds you want, you get the moisturizing you want, and then the rest of it you put canola oil in there. You make a cost-effective bar of soap. By saponifying it, and I may stop right here. Boy, we got a lot of time. How am I so far ahead of things?
You said you need 2 full days for 18?
Yeah, I need 2 full days for 18.
We only have Monday and Wednesday. And we're taking the test on Wednesday, right?
Not next week.
Oh, the following week of
Do we have next class Monday?
The 6th to 18th.
We're taking the class the Wednesday before Thanksgiving.
Oh, okay.
Wednesday before Thanksgiving.
Do
Okay.
we have
We're
a class for Veterans Day?
On what? Yes. But you can have the day off on Thanksgiving. All right, I'll just try to make it easy. And take the next day off too. Thursday and Friday, you get off. And Saturday and Sunday. And we're going to try to give thanks for that. Yeah. Hang on here a second. See how many slides do I have to go? I tell you what, we'll pick up on this on Monday, and I'm going to give you chapter 17 homework right now.